Hello there, and welcome to the last section in Chapter 10. This is Section 10.4. We're going to see how to apply everything we've discussed in the previous few sections on Taylor series. Okay, so looking at this first question, this is really just tying up a loose end. Now we've seen this result that e to the x is equal to the series 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on. And we have equality here for all x. But we have not proven this result, okay? That's our job for this question. It says, use Taylor's remainder theorem to show that e to the x is equal to this series for all x by showing that the remainder, Rn of x, which by definition is the difference between e to the x and Pn of x, where Pn here is the nth Taylor polynomial of e to the x centered at a equals 0. Okay, we're supposed to show that this remainder approaches 0 as n approaches infinity for all x. Okay, so there's a lot to unpack here. Let's just take things one step at a time. So first, recall from section 10.1 that Pn of x, the nth Taylor polynomial of e to the x, centered at a equals 0, is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on up until we get to the degree n term, which is x to the n over n factorial. Okay, now our job is to show that the limit as n approaches infinity of Pn of x is equal to e to the x. Okay, and we're going to do that using Taylor's remainder theorem. Okay, so let's recall what it says. Okay, so if I have a function f here, and I want to approximate the function value f of x with this Taylor polynomial Pn, right? So here the exact value is f of x, that's the height on this blue curve, and my approximation is the height on the red curve, that's Pn of x. And now the error in my approximation is what we're calling the remainder. This is Rn of x, and that's that little gap there you see in yellow. Okay, now what Taylor's remainder theorem says that error in absolute value is bounded above by this quantity m over n plus 1 factorial times x minus a in absolute value raised to the n plus first power. And recall that m here is an upper bound on the n plus first derivative of f in absolute value on the interval I, where I is an interval that contains the center of Pn of x, that's this number a, and it contains x. All right, so our goal is to show that Rn of x, this error term, approaches 0 as n approaches infinity for all x. Okay, so let's go to a visual here to help us think about this. All right, so here in red is our exponential curve, and then in blue we have our Taylor polynomials. Okay, and as we see, increasing n gives us better and better approximations to the exponential curve. Okay, now our job, to be a bit more precise, is to say, all right, if I choose any x, I want to look at this gap between the value on the exponential curve and the value on the Taylor polynomial. And this little segment you see in green here, that's Rn of x. That's the error in our approximation. Okay, and we're needing to show that as we let n approach infinity, this gap, this error, goes to 0. Okay, so if I let n increase, I can see that that error goes to 0. Now I need to show that this happens for any choice of x that I make. So for example, if I choose x over here, right, where the gap is bigger, well, if I let n approach infinity, right, that gap should still close to 0. Okay, what if I chose x, say, over here? Well, let n increase to infinity, well, again, it's going to approach 0. Okay, that's our main goal. Now, why does showing this imply that e to the x is equal to this series? Well, if e to the x minus Pn of x approaches 0 as n approaches infinity, that implies that e to the x is equal to the limit of Pn of x as n approaches infinity. And Pn of x here, right, this is the partial sum of this Taylor series. And so in turn, we would have shown that e to the x is equal to this series here. Okay, so that's our job. Okay, now our game plan here, we're going to do three things, okay? The first thing is we're going to just fix a value of x, and this can be any value on the real number line, right? We need to show that Rn of x approaches 0 as n approaches infinity for all x, so our argument needs to work for any possible x that we choose. Okay, then if I want to apply Taylor's remainder theorem, I need an interval I that contains the center of the series, which in this case is a equals 0, and it needs to contain this number x that I've selected. So I'll go ahead next and choose an interval I that's centered at a equals 0 that contains this number x. And then the third thing we're going to do is apply Taylor's remainder theorem to show that Rn of x approaches 0 as n approaches infinity. Okay, so this is the game plan in establishing this goal. All right, so now let's go ahead and carry out the plan. Cool. All right, so here is our exponential curve. All right, so first thing we're going to do, choose an x. Okay, and it can be any number x on the horizontal axis. Next thing we're going to do is choose an interval centered at a equals 0 that contains x. Okay, so I'm going to just choose this number c so that x is contained in this interval from negative c to c. All right, then what am I going to do? I'm going to apply Taylor's remainder theorem on this interval. Okay, now here the remainder theorem says that this difference of e to the x and Pn of x in absolute value is bounded above by m over n plus 1 factorial times x minus a, but here a is 0, so it's just absolute value of x raised to the n plus first power. Okay, now how do we find m? Well, I want the n plus first derivative of e to the x. Well, that's just e to the x itself, right? So now what I'm asking is, how big can the absolute value of the n plus first derivative of f, in other words, how big can the absolute value of e to the x be on this interval I? And here's a graph of e to the x. Note I can drop the absolute value here because e to the x is strictly positive for all x. So where does this thing find its maximum? It's going to find its maximum, right, at the right endpoint at c. So we conclude here that m is equal to e to the c. All right, so then let's go ahead and plug that in. Right, we have then that this difference in absolute value is bounded above by e to the c over n plus 1 factorial times the absolute value of x raised to the n plus first power. All right, now how big can x be on this interval? Well, right, we selected c, so this interval contains x. So notice, right, the largest this quantity, x to the n plus 1, right, an absolute value, the largest this thing could be is c to the n plus 1, because I know that x is less than or equal to c. And so putting that all together, this difference in absolute value then is bounded above by e to the c over n plus 1 factorial times c to the n plus 1. All right, we're getting there. So now what do we want to do? Well, let's take the limit as n approaches infinity. Okay, note here that e to the c is constant. So what happens to this expression in blue, the c to the n plus 1 over n plus 1 factorial? Well, if you go back to sections 9.1 and 9.2, we actually looked at a few problems like this. So we looked at a problem where we had the sequence 4 to the n over n factorial, and we argued why that approaches 0. Okay, the loose explanation is that this exponential term up here is going to grow to infinity at a slower rate than this factorial term in the denominator. Okay, so this thing right here is approaching 0 as n approaches infinity. And since Rn of x, right, is bounded above this thing in absolute value, that implies that Rn of x must then approach 0. Okay, so that's exactly what we set out to establish. So now let's go ahead and draw our conclusion. Our conclusion is that since Rn of x is approaching 0 as n approaches infinity, and this is true for any x that we select, okay, as we mentioned earlier, right, it follows that e to the x is equal to the limit as n approaches infinity of Pn of x, which is then equal to this series. And here I've just written that series in sigma notation. All right, so that completes the proof. All right, now if you look on the 10.4 worksheet, okay, at the top there on the front page, I've listed a bunch of common Taylor series, right? You can see the series for e to the x right here. Okay, now similar arguments can be made to argue why the sine of x is equal to this series and the cosine of x is equal to this series. Note for the natural log and arctangent, we actually did these in the previous section. But if you're curious, okay, in the textbook they go through the argument for sine x using a similar Taylor's remainder theorem technique. So definitely check that out. But what I want to say now, before we press on to the next video, is that for the rest of this section, okay, you can assume these results, okay? Now the game plan is just to start using them, okay? Cool, well, that's a good place to stop. I will see you in the next video.